Okay, so welcome to today's class. We are still discussing about high resolution NMR spectra of molecules. In the last lecture, we started with the explanation of interpretation of multiplet structures using first order analysis, and then we looked that in these multiple patterns in different groups of line how it arises, what could be the basis of relative intensity, that is what we started with, and measurement of coupling constant from these splittings of individual group, and that helps in identification of different groups having the coupling constants. And then we started looking at into the basics of quantum physics concepts. We looked at various terms like what is the operator, what is the eigenfunction, Hamiltonian and eigenvalues. So, we were at the stage where we wanted to discuss the two spin system, like let us consider a AB system. AB case like two spins which have a close proximity of chemical shift, and that is what we define as a AB system. So, both of these spins let us consider they are half spins. So, I is half for both of these spins. Then for such spins we can write the, so angular momentum I is half, and then we can write it the Hamiltonian, which will be given by these terms where gamma is the gyromagnetic ratio of spin 1, the H1 is the Hamiltonian corresponding to that, and IZ1 is the eigenfunction for spin number 1. Now similarly these terms are for spin 2, and then there is a term which arises because of these two spins are coupled, and therefore J is the coupling constant between these two spins. Okay, so total Hamiltonian if these two spins are coupled through bond will be given by these term overall, where the contribution from first term is this, second term is this, and then because of the coupling between these two terms is actually J I1 I2. So, if you look at the resonance frequency of these two will be given by frequency of 1, frequency of 2, this is coming because of these two spins are coupled through the bond. So, this is the Hamiltonian, resultant Hamiltonian for an system, two spin system both having half spin. So, now for such system we can write the basis set for 4 product function, and these, like as we said, the two spins are there. So, both either can be in alpha alpha state, that is one basis set, the another basis set can be both are, one is in alpha state, another is in beta state, the third one is beta state, alpha state, and fourth one is in beta beta state. To simplify that, let me draw this. So, this we define as say alpha alpha state. So, this is alpha alpha, both states having up spin. One is alpha and the another is beta, like alpha beta spin, or it can be beta alpha spin, and then other can be here beta beta spin. So, these are 4 basis set, and these functions are orthogonal. That means if you take product of this alpha 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 beta, one can write it like this, and that will be 0. Okay, so these are the 2 spin system case. Then we can go and define the eigenfunction for this operator Iz, alpha beta eigenfunction for operator Iz, and one can calculate the element matrix, and if we calculate we get these term H11, and then we can solve this equation. So, we get essentially the frequencies term here and the coupling term here. So, these can be solved. So, this is saying that frequency of 1 and 2 divided by 2, so that comes at the center, and we can solve this equation by something called matrix element Ix and Iy by making use of the raising and lowering operator. This is typically used in the quantum mechanics to solve such equation. So, here one can define Ix will be I plus I minus divided by 2, and Iy will be I plus minus I minus divided by 2I. So, if we go ahead and solve this equation, What we can find it for these operators, the following property will arise, that means I plus alpha will give you 0 and I plus beta will give you alpha. So, this is like this lowering and raising operator. So, this is raising operator. So, that means beta will be raised to alpha state, and here it is a lowering operator. So, alpha will be lowered to beta state. So, like say up state, that is alpha state, will be lowered by this lowering operator to beta state, and here I plus is applied to beta state. So, this is a beta state and it will be raised to by raising operator to alpha state. So, that is what. So, one can calculate now the Hamiltonian elements H11, which will be given by mu 1 plus mu 2 divided by 2, and the coupling constant which comes from the because these two spins are coupled. So, that will be J by 4. So, H11 will be mu 1 plus mu 2 divided by 2, that is the average frequency of these two, plus the Hamiltonian terms coming from the coupling constant, that divided by 4. Similarly, one can calculate the other terms of the matrix. So, here the other term H12 will be 0, H13 again will be 0, H14 will be 0, and if you look at here the point to pay attention, the H22 will have value, and that will be actually that minus J by 4. So, earlier it was plus J by 4, now minus J by 4, and similarly here you have minus J by 4, and here that will be negative, that will be plus J by 4. So, now by solving this equation we have non-zero term, and there are here J by 2 also term, here J by 2 term. So, if we solve this equation, we get this block diagonalized representation of this matrix, where these are the 4 elements that we are getting it. One element H11, H22, H33 and H44, and here because of the mixing of these states, H23 and H32 are also populated. So, these are the spin states that we are talking. Here is for alpha alpha, this one for alpha beta, this is for beta alpha and beta beta states. So, these 4 states we can represent our Hamiltonian in simplified form, in block diagonalized form, to get the eigenvalue of these Hamiltonians. So, okay, if we do that, and then we can write the eigenvalue coming from solving of these equations. So, we get 4 eigenvalues, one for state 1, that is alpha alpha state here, and then we have for alpha beta state, beta alpha state and beta beta state. So, these 4 states that we were talking in the previous slides, these 4 states we are getting the eigenvalue of these states. Now, eigenfunctions of these states, one can write it out, Hamiltonian H applied to alpha alpha state, we get the eigenvalue is E1, and similarly for the other state E2, E3 and E4. So, phi 2 is actually cos phi alpha beta and sin phi beta alpha. So, one can solve this, and these two terms are coming because these two spins are mixing because of the coupling between them. So, 2-3 terms are coming because of the mixing of the states. Fine. So, these are the states. So, as we defined, so let us take a simplified version of this. So, here we are talking the energy level coming because of states, and in the previous slide we calculated E1, E2, E3 and E4. So, where are those? Here. So, alpha alpha state say gives E1, and here we have E2 and say E3 and E4. So, these are states alpha alpha for proton proton coupling. Here one can take it also carbon proton, but this is not a AB system, but anyhow here this is the kind of 4 states that we are giving. So, here in this case now we define the 4 energy states for such system. Now, as we know that these transitions that will happen between these system will follow the selection rule, and selection rule in this case that delta m should be plus minus 1. So, that means transition will happen 1 to 2, here one state to state 2, and that means this transition will be alpha alpha to alpha beta states, means here second spin is flipping. The next transition we are talking is 3 to 4, So, in this case what is happening, beta alpha changing to beta beta. So, here again second spin is flipping. So, this flip is happening here, again this flip is happening. So, these are the two states, and now for these the other spins 1,3 transition and here 2,4 transition is happening. So, in this case 1,3 transition alpha alpha first spin flips to beta, and here again alpha beta, here first spin flips to beta states. So, the spins that flips is called active spin, and spin that does not flip is called passive spin. So, this is energy state that we are talking about in the previous slide. Now, let us go back. So, the extent of this spin, as we saw that it has a J term in the previous slide, we looked at the energy level has a J term. So, the extent depends upon the relative magnitude of the coupling constant, how much coupling constant is there and what is the separation between the chemical shift of these spins. So, here J by delta is actually J is the coupling constant and delta is the difference in the chemical shift. So, larger the J by delta again I am telling you it is a coupling ratio of coupling constant with the separation in the chemical shift. So, stronger, then mixing will be stronger. So, the mixing of two spins will be stronger, and if it is less then it will be lesser. So, if J by delta is approximately 1, this is called a strong coupling case, and if J by delta is less than 1, it will be called a weak coupling system. So, AB kind of a strong coupling system, because here this shift, the difference in the chemical shift is small. However, X kind of a system is called weak coupling system. Here the separation in these two chemical shift is quite a bit. Now we know the energy of these states, now we know the eigen function of these states and where transitions are happening and what is the probability of transition that one can calculate. So, then one can calculate the one can get the frequency value of each of these transitions that we talked about and what will be the relative intensity of these transitions in various case. So, say transition 3 to 1 that we defined in the previous slide, 3 to 1 is like here, one of these 1 to 3 or 3 to 1 here. So, that transitions will give us the frequency like this, here C is a constant. So, that relative intensity will be 1 minus sine 2 delta, then 4 to 2 will be actually this term will be frequency minus J by 2 C, and that will be intensity will 1 plus sine 2 delta. 2 to 1 will be again here, these will be added and plus, and then constant C here, that will be 1 plus sine 2 theta, and 4 to 3 will be transitions like this, where sine 2 delta can be explained in this term, where this is the chemical difference in the chemical shift, this is the coupling constant value. So, for these transitions as we mentioned psi 1 to psi 2, psi 3 to psi 4, each of these transitions one can get the frequency that comes and get the relative intensity that coming because of these transitions. Okay. So, as we looked at for weak coupling system, sine 2 theta is 0, that means all the transitions are going to be of equal intensity. We go back here, and if sine 2 theta is 0, that means we are going to get 1 1 1 1 value. Okay. So, that means for weak coupling system something transitions happening like this, here 4 transitions that we were discussing a minute ago. Now, 1 to 3 transition, 2 to 4 transition, 1 to 2 transition or 3 to 4 transition, in each of the case intensity is going to be equal, and the actually the chemical shift center will be of say spin 1. Okay. So, in this case alpha flips, here beta flips, in this case alpha flips and beta flips. So, these spins 1 and 2, this will be the case for equal intensity, and that is the case for weak coupling system as we have shown earlier. So, here we are talking about spin 1 for both of these case, and the equal intensity pattern will come. So, here will be the center for frequency 1. Now, A will be called active spin because this spin is flipping, in this spectrum, and X will be called passive spin, this spin is not flipping. If you look at here, whatever transition we are seeing here, either this transition or this transition or even this transition or this transition, what is happening here? Our delta m is changing by plus minus 1, either this transition or this transition. This is allowed transition in NMR according to selection rule. Now this is not only transition that is possible, there are some other transition that is possible. So one of these transitions can be something like this, say this transition. Now what this transition is? What is happening here? Actually both spin A and X are going from alpha alpha state to beta beta state. Both spin are flipping, that means the delta m is here 2. This transition is called double quantum transition. 2 quantum, one from spin number 1, another from spin number 2, both are flipping. So that is called double quantum transitions, and there are another type of transition can also possible like here. Here first A spin is flipping and also the X spin is flipping. Since now this is happening, both spins are flipping. So this is called 0 quantum transition because there is no resultant delta. So here delta m value is 0. Now this is 0 quantum transition. So generally double quantum transition or 0 quantum transitions are not allowed. So you remember, this is not an allowed transition, double quantum transition or 0 quantum transition in NMR. However, using some trick one can exploit this transition. So these are generally called forbidden fruit of NMR spectroscopy, and there is some benefit of that because of relaxation parameter, that again we will come later. Now coming back to the intensity parameter. So as we discussed few slides back here, that theta parameter. So we looked at sin 2 theta is 0, that means this is a weak coupling system and all intensity of all 4 transitions are of equal intensity, but suppose it is not 0, then what will happen? So the parameter theta manifests the presence of a strong coupling, and then that alters the intensity of frequency of the transitions. So now we have like simulated this spectrum. So if you say the ratio of J divided by this delta changes, then the intensity and the pattern changes. Now let us start with a simply like this, J divided by this delta is infinity, that means J is very large compared to delta. So that is why we are having infinity value. Now for such case we get a single transition. What I mean, J is very large compared to difference in the chemical shift, that means they look like or they are equivalent spins and therefore no splitting will happen. So they are called magnetically equivalent spin where there is no splitting happening. Now as we start changing here the ratio J by delta, if it becomes 2, you see the splitting pattern starts originating. Now this will split into 2, very small here, and then there are 2 others that are coming here. Now if the chemical shift difference and J becomes equal, then we get a 4 peaks. 2 central transition peaks are very intense compared to the 2 outer one. As we start decreasing this ratio, as we go from 0.5 to 0.33 to 0.25 to 0.1, we see the separation is now changing, and here are the 2 central. So this is the case of weak coupled spin. Okay. So here the chemical shift difference is 10 times more than the coupling constant, then peaks will be like this, 2 spins separated, and now this is the J value between these 2, and these are the resonance frequency of A spin and B spin. So this is weak coupling spin, this is magnetically equivalent spins. Rest other are for strongly coupled spin. As we go from here to here, the effect are pronounced and the outer peaks becomes more intense and the central peaks get less intense. So if you look at the pattern of this splitting, they have a something like a roof effect. So this is coming because of the strong coupling case, this is called roof effect of the splitting, and this arises because the strong coupling in the AB system. Okay. So, that is what we discussed. As J by delta is infinity, that means two spins are equivalent and the outer two transition would have identical 0 intensity and inner two transition would have same energy. So, the coupling between the equivalent spin does not lead to splitting in the NMR spectrum. So, like if you look at CH3 in methanol, so it will have one, like for these actually these are equivalent spin and they will have only one peak. So, they are magnetically equivalent spins and does not cause splitting of the line in NMR spectrum. Okay. So, to summarize what we saw that what is the effect of strong coupling. Because of the strong coupling, spins loses their identity and the transitions cannot be described to a particular spin system. So, the analysis in this case becomes little complicated. The transition will have a different intensity as we saw in the previous slides. Because of a strong coupling, there are two outer peaks are of small intensity and two inner peaks are of greater intensity, and the product function corresponding to the same total value of J component that get mixed. So, that is the case also for strong coupling, and the chemical shift of spin cannot be determined by simple inspection of the spectrum. It requires more rigorous analysis. That is what is the effect of a strong coupling like AB spin system. Okay. So, now we looked at the two spin system. Now, we move to next NMR spectrum for 3 coupled spin system. So, let us take 3 spin coupled spin system where say spin 1, 2 and 3. They can be coupled in 2 manners. One manner can be A is coupled to B and coupled to C, or one can, if they are weakly coupled, we can say A is coupled to M coupled to X. The another case will be cyclic, 3 coupling constant here. A will be coupled to B and B is coupled to C and C is coupled to A. So, all are coupled to each other. Now, these two can be possibility for 3 spin system. So, all spins may be non-equivalent and weakly coupled, like as we say weak coupled system we can define as a AMX system, or it can be 2 spins may be equivalent and weakly coupled or strongly coupled to third spin. So, say these are say AB2 kind of system. Now, third case can be all spins may be non-equivalent, 2 of them may be strongly coupled. So, ABX and here we can have AB2 kind of system. And the last one, all 3 spins may be non-equivalent and strongly coupled. So, that will be ABC kind of a system. So, AMX system as we defined is weakly coupled spin. So, again to remind you what we mean by AMX system, like their chemical shift, if you look at A comes here, M comes here and X comes here, that is why their chemical shift is separated and that is why we called it AMX system. On contrary, AB system is a strongly coupled system. So, this may act to weakly coupled system at higher field. So, AB system, that what we mean that in the chemical shift range A is coupled to B is coupled to C, but this is say at one field. What will happen at the higher field? If you put the higher field, A will be here, B will be here and C will be here. So, now they will start behaving like a weakly coupled system. So, if they are weakly coupled system, then what will happen that each one is split. So, here first say, so there are 3 spins here as we described 1, 2, 3. So, first this spin is splitted because of 1-2 coupling. So, here are that coupling and then they are splitted because of 1-3 coupling. So, resultant are 4 lines for say spin number 1. Spin number 1 now is splitted into 4, first because of 1-2 coupling and then because of 2-3 coupling, but this is the case for the weakly coupled system. Now, let us look at this system here like a 2 spins will be equivalent and weakly or strongly coupled to the third spin. So, this kind of a AB2 system. So, if we write eigen function and energy for such case using same quantum mechanical trick that we discussed a few minutes back. So, now what we get is now here AB system. So, two these spins are equivalent and they are strongly coupled to a system. So, what we have is half of frequency of A, then B, and then because of the mixing of AB and 1/4 of BB, that is one eigen function. Then we have another eigen function. So, here frequency of A and coupling constant between BB and so forth, one can write it. So, here the term M will be given of this chemical shift of AB plus half of the coupling constant between them. So, we can derive energy for all these states, and then one can start looking at what we get the spectrum. So, if we do rigorous analysis, we get a spectrum for A B2 system like this. So, if the J by delta is infinity, then we get actually one peak as we say equivalent. So, this will be identical spins, but as we start moving, what we are seeing that splitting pattern changes, and if we have something like J by delta 0.5, we have like 9 lines here, and as we move here we can get even more splitting pattern like this. So, here one thing, if you notice that we are discussing the spectral intensity are like this, and this is called roof effect in the chemical shifts. So, because of this strong coupling, this roof effect appears. Because of weak coupling, as we saw in the last slide, all are of equal intensity. So, that is the A to B system, and this was simulated for AB spin system, where we consider JAB, the coupling constant between A and B, to be 10 Hertz. Okay. So, that was AB system. Then next we can look at the ABX system. ABX means A and B are strongly coupled, but they are weakly coupled to X. So, one can write the energy function for each of these states alpha alpha, alpha alpha beta. So, what I mean by alpha 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 is something like this, and alpha alpha beta is something like this, and as you go down beta 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 is like this, beta beta alpha is like this, alpha is like this, and intermediates all those are mixed state because of the coupling constant. So, in that case we have the spectrum that will come out to be something like this. So, here one can see because of AB a strong coupled system, we have again a splitting pattern as we discussed earlier. It will have this roof effect of various transition 1, 2, 3, 4, 5, 6, 7, 8, and now here they are weakly coupled to X. So, they will split X, and if you look at here, because of JAX plus JBX, this gives another 4 lines, and these two very small lines here, but one can see here intensity are more or less equal, but there will be some effect. So, X part of ABX system comes like this and AB part comes like this. Okay, so, here we have assumed that AB coupling constant is 15 Hertz, AX is 1 Hertz, that is and BX is 10 Hertz. So, that is how a spectrum will look like for a strongly coupled at AB and they are weakly coupled to X system. Okay, so, one can expand and one can find it out these different spectrum for X spin and also for X spin and also for AB spins. So, this is the kind of a spectrum for one can get it for a strongly coupled AB system that are weakly coupled to B spectrum. So, these are some of the rigorous analysis, and as we looked at that these spectra where they are strongly coupled, they are not easy to interpret. So, what one trick one can apply, that these are strongly coupled system and the coupling constant remains same. So, one option is to take these molecules and start recording the spectrum at the higher field. Now, chemical shift separation between them can increase, and maybe they will convert to some of the weak coupling system, and then one can start analyzing this spectrum. So, today I am going to stop it here, and in the next class we will try to go little more detail, look at the effect of these couplings on the dynamic process or the chemical exchange process, and we can build up the concepts from here. Okay. So, thank you very much and looking forward to have you in the next class.